Alright. So like I said, we're talking about inverse trig functions. And this one receipts. I think I grabbed the wrong marker yesterday.
Maybe the marker thinks you stink.
It probably does. Maybe this one works. Yep. We are for now skipping over section 6.3. We will revisit it. Actually, we might not revisit it. We'll probably just cover that stuff when we go in chapter 5. We're skipping 6.2 or 6.3, going from 6.2 to 6.4. If you're following along in the book or anything like that. All right. So what we've seen beforehand is an example like this maybe. I've got a triangle with some angle, and I'm given some information about the triangle, for instance this, and I'm told maybe cosine of theta adjacent is 3/5 or something like that. Or I'm told to figure out some sort of problem where I have maybe a building and it's casting a shadow at an angle of like 30 degrees, and I know the shadow is 50 feet long, and so I'm told to find the height of the building. And to do this, I say, okay, well, I have my building. The information I have is my building, or I don't have my building, so that's the information I need. I have my angle is 30 degrees. This side right here would be my adjacent side to this, equals 50 feet. The information I don't have, that's step 1 of our process, step 2, is this B, the opposite side, B. Step 3, a formula to connect those two. Well, what connects adjacent, opposite, and angles? Which of the 3 trig formulas does that? Tangent. I have tan theta equals opposite over adjacent. Plug all of my stuff in there for step 4 of our 5-step process. So opposite is B. I have, okay, so tan of 30 degrees equals B over my adjacent 50. And then step 5 is solve. So I have B equals 50 tan 30 degrees. And you punch that into your calculator and get some sort of result. I did not grab my calculator, and I don't have my phone to use, so that's fine. You can put that in your calculator and figure out what the answer is. So just a very, very quick review of basically what we did yesterday and Tuesday, where we did right triangle trig, and then we walked through problems with the 5-step process. Any questions about this? This example, basic right triangle trig, or the 5-step process, or anything like that? All right. Cool. I'll let y'all copy this down for another second. And again, if you're worried about copying everything down, it's in the lecture recordings, and I type all of these notes up. I'm still in the process of typing the notes for this section up, but they should hopefully be done by the end of the day, although my day is a little packed. Now say, for instance, we're given information about a triangle, and we want to figure out the angles of the triangle. For instance, let's revisit this triangle. And all I tell you is that this is 4, this is 5, and I have some sort of angle. Right, maybe this is I have a 4 foot tall shed or something like that. I've got a 5 foot ladder leaned up against it. What is the angle that the ladder is at? And we could use this too. If this was possible, then we have to know what this is. We don't care about it. Cool. So how do we figure that out? Well, take our 5-step process. What do we know? We know this opposite side is 4, and we know this adjacent side, or not adjacent, hypotenuse, is 5. What we don't know is the angle theta. We don't really care about this adjacent side, we just care about the opposite of the hypotenuse. So we don't need to write that we don't know the adjacent side. 3, what is an equation that relates opposite, hypotenuse, and angle? Sine, right? So, SOH. I have sine theta equals opposite over hypotenuse. I go to step 4, which is plugging my known stuff in to figure out my unknown stuff. So sine theta equals 4 over 5. And step 5 is to solve. But how do we solve for theta here? All right, we can't just divide by sine or anything like that. Sine is a function. It's just like if I were to say, x squared equals 9, how do I solve for x in this situation? How would I solve for x here? Square root. Right? The square root is the inverse of the squaring operation, right? When we talk about functions, functions are things that take stuff from what we call a domain and spit it back out into what we call, I put all the elements outside of it. Spit stuff out in what we call the range. Who remembers this from algebra? Domains and range. And what the function does is it takes a point and maps it to a point. F. Takes a point, maps it to a point. Maybe this is f of some x, this is f of some other x, so on and so forth. And that's what a function does, is it maps all of the points from one thing to another. Maybe not all of the points, and that's a little technical, but it does that. What the inverse function does then is it goes the opposite direction. We map something from the range back to the domain. So this might be f inverse of x1, f inverse of x2, so on and so forth. So it goes backwards. For example, when looking at the square operation, its domain is all real numbers, and its range is specifically all positive numbers, right? I can't have a negative number be the square of something unless we're talking about complex numbers. So it goes from real numbers to positive real numbers. Then the square root function takes in positive results and spits out technically only other positive results, but it maps me back into the domain. So it takes elements from the range, which were the positive things, and gives me back some of the information here. It doesn't give me all the information because it's not what we call injective, but we don't have to worry about that. All right. So now we want to do the same thing for this, and that's where inverse trig functions come in. When we talk about our big 3 trig functions, those are sine theta, cosine theta, and tan theta. They all have their inverses. A lot of people write them with the word arc in front of them. So arc sine theta, arc cosine theta, and arc tan theta. But how I will almost exclusively write them is just using inverse. Sine to the negative 1 theta, cosine to the negative 1 theta, tangent to negative 1 theta. This does not mean take the reciprocal, right? It is not true that tan negative 1 of theta equals 1 over tan theta, right? This negative 1 only means reciprocal if we're dealing with numbers. When we're dealing with functions, it's the inverse. So that is not true. It is not true that they are reciprocals. Remember, we all had an entire set of functions that are the reciprocals. Cotangent, secant, cosecant, which we talked about on, was it Tuesday, I think? So we have those, but that's not what we're dealing with. We're dealing completely new functions. So we're going to have the inverses. The inverse is what I apply to both sides to get rid of this sign. So right here, I have that sine theta equals 4 over 5. And to get rid of this, so I have just theta, I apply inverse sine on both sides. So the sine cancels out the inverse sine. I'm left with just theta. I have that theta is equal to the inverse sine of 4 over 5. And then that's something that you can punch into your calculator. Who has ever seen anything like this before? A couple of y'all. Who has seen, in general, inverse functions? Functions that invert something. You have all at least seen the square root function, I really, really hope. So you've at least seen one example of an inverse function. Now we're going to be dealing with a set of 3 inverse functions. Technically 6 inverse functions, because we can take the inverse functions of cotangent, cosecant, and secant as well. But we probably won't do much of that. Cool. So then I have theta is the inverse sine of 4/5. You can punch that into your calculator. All of y'all's calculators should have the inverse sine button. I again did not bring my calculator. But you can punch that in and then get your result. For now, I'm just going to leave it as an exact result. Theta is the inverse sine of 4 over 5. One thing to note is that these inverse functions have a restricted domain. There's only so many values that I can put in where these functions are defined, right? There's only so many possible outputs for sine, cosine, and tangent, right? Sine and cosine are restricted to be between -1 and 1. Let me write that. So sine maps the real numbers to the interval -1 to 1. Cosine maps the real numbers to the interval -1 to 1. Tangent is a little weird. Tangent maps, what does tangent map specifically, so I don't confuse. Any real number that is not a multiple of pi over 2. A whole multiple, I should say. And can spit out any value. This is the set builder notation that you probably saw in algebra. It's just saying that all real numbers without every whole multiple of pi over 2. So for example, 3 pi over 2, -10 pi over 2, those are not included in that. If I were to try to take the tangent of pi over 2, it's undefined. And we'll see why that's the case in about a week or so.
the equivalent is 0?
No, it's undefined.
Oh.
Yeah, tangent of pi over 2. So, as a brief aside for anyone who's seen trig before, pi over 2 is this point, which is 0, 1. Sine is equal to f or y over x. So y. So that would be 1 over 0, which is undefined. Or not sine, tangent, I mean.
Okay.
So you get an undefined value at every multiple of pi over 2 because you're dividing by 0. It's equal to 0 at every whole multiple of pi instead. So 0, pi, 2 pi, all that sort of stuff. But y'all don't have to worry about this, at least not for a little while. That was more just to address this question there. All right. Any questions about this? About inverse sine in general? So I mentioned this. That means that the inverse functions also have special domains and ranges. This is possibly just something to keep in your notes in case the homework asks you questions about this, but I'm not really going to ask you a question about this on an exam or anything because it's not really anything that y'all need to know. So the inverse sine takes as inputs -1 to 1, which makes sense. The output of sine is -1 to 1, so all my values of sine should be -1 to 1 going into inverse sine. And it spits out anything, from minus pi over 2 to pi over 2. And it equals pi over 2. Right? This is an angle in radian, so this would be the same thing as saying it spits out values from 90 degrees to -90 degrees. So it spits out, like if I'm looking at a circle, it spits out any of this information. Those are the possible y values, essentially. Just to visualize it. Inverse cosine takes as its input the output of cosine, so I'm just switching that part. But it's instead now restricted to all of my possible x values, which would be from 0 to pi. Is that what I wrote? Again, when we start talking about the unit circle and everything, this stuff will start to make a little bit more sense. As for now, this is more something just either to write down or look back at the lecture recording I have. And the inverse tangent takes in as its argument the real numbers, right? So my output was the real numbers. And spits out -pi over 2 to pi over 2. So it spits out something that is in that top arc right there, but does not include the pi's over 2. That just might be useful info to have if there's a homework question about that. So now a somewhat related question that I could ask y'all about inverse sines and inverse cosines maybe. Is what are all of the angles between 0 radian and 2 pi radian such that sine of that angle equals -1/2. So that's a question that you could be expected to see maybe on a test or something. And so you have to figure out, okay, well, how do I solve this? Cool. Well, I'm given sine theta equals -1/2. I'm asked to solve for theta, what would I do to both sides to get theta alone? Inverse sign. I just want to undo this sign right here. And give myself some space there. So I take the inverse sign on both sides. I cancel this out. So I get just theta. And that's equal to the inverse sine of -1/2. Now I can interpret my answer in the calculator, but before I do that, I have to realize that I asked the question in radian. So you need to make sure your calculator is in radian. So what I do here, punch in my calculator, I should get -1/6 pi, so minus pi over 6. I believe is the answer there. But is that between 0 and 2 pi? Is -pi over 6 between 0 and 2 pi? No, it's not. So how do I make this between 0 and 2 pi? Right? Remember we talked about coterminal angles? Coterminal angles all have the same sines, cosines, arc cosines, all that sort of stuff. So to get this between 0 and 2 pi, I could just add 2 pi to it. And I'll get 11 pi over 6. And is this between 0 and 2 pi? Yes, it's slightly less than 2 pi. 2 pi would be 12 over 6, so this is a little less than that. So this is indeed in 0 to 2 pi. Again, if you don't remember from college algebra, this symbol right here means in, so it's in this interval. Any questions about this? Any questions at all? Yes?
Why can you just add 2 pi?
Because they're coterminal. Remember that angles are coterminal. Say for instance, this angle is coterminal. Oh, that doesn't have any ink in it. This angle, maybe theta, is coterminal with an angle that would wrap around and is the exact same thing. Maybe this is phi or something. Angles that are coterminal have the same cosine, sine, tangent, all that sort of stuff. Remember when we were defining cosine, sine, and tangent, we just drew a triangle here. Since this is in the exact same point, it forms the exact same triangle. The angle has just wrapped around one more time. So we can add either 360 degrees or 2 pi radian to the angle measure, and we get the exact same value. So these angles are basically the exact same thing. It's just that this one is positive. It's between 0 and 2 pi. So it gets rid of this negative part. So that might be an important thing to write down in your notes. Coterminal implies the same sine, cosine, tangent, secant, cosecant, and cotangent. They have all the exact same values that we're worried about. The only difference is it's a different angle, so it's wrapped around a little bit more. Any questions about that one? Yeah, let's all write this down. The beginning of this class, or a lot of the beginning of this class, is writing down vocabulary and memorization. I apologize for that, but that's kind of all that trigonometry is. And then getting used to drawing triangles and circles. Clearly I don't do trigonometry enough because I can't draw a circle to save my life. Or triangles, really, they're pretty bad. Yes?
The -pi6 means that the angle is going clockwise instead of counterclockwise?
Exactly. So the angle is going clockwise, but this question specifically asked, okay, I want to think about counterclockwise around the entire circle. So we had to do a little bit of adjusting. But this is in the exact same place. It's just now it's been given as a positive result. It is kind of funky for y'all to be doing a math problem and think, okay, well I got an answer, how is that any different from this answer if every answer has to be true? Well, these are the exact same thing technically, but kind of not the exact same thing because one has been wrapped around the circle one time. So think of it kind of like a minute hand. If the question was asking about what minutes, this is fine, but then the hour might be different. If I've wrapped the minute hand around the circle, the minute hand is in the same place, but the hour hand has been changed a little bit. So an equivalent question, if I were asking you about a clock, would be like, what time is the minute hand facing completely down if the hour is 5 o'clock? Right? So the minute hand is facing down in a lot of places. Every something 30 it's facing down, but specifically the hour is 5 o'clock, the only answer is 5:30. This is a very similar thing. This is asking which of the angles points over here, specifically if it's between 0 and 2 pi. There's only one answer, this 11 pi over 6. So I could instead ask you, what are all the angles such that sine of theta equals -1/2? Then I don't have to worry about this plus 2 pi. It can be any angle that's coterminal with this. So instead I would write, instead of just 2 pi plus 2 n pi, where n is any integer. Then all this spits out for me is every coterminal angle with our point minus pi over 6 looks something like this. So it spits out every single rotation I could do to get a point on this part of the circle. Cool. For how many of y'all this doesn't make sense because you don't see the point in having to make a bunch of different angles? Like, why do I have to care about where the angle's at if it's the same angle, it's the same angle? A lot of people, they don't get mathematics because they don't see the motivation behind it. And this is one thing that I definitely understand why you wouldn't see the motivation behind it. Unfortunately, there's not much motivation behind I told you to, so you have to find it. It does become important when you have to go do things like electrical engineering. Electrical engineering very heavily relies not only on trigonometry, but on complex functions. And so the way you represent your values of a certain point, like if you're doing wave analysis or anything, that actually does matter a little bit. So anyone who has to go take, a circuits course or anything in electrical engineering, this does matter a little bit more for you. Cool. Any questions about anything that's on the board or anything I've said in the past 30 minutes? Am I good to erase the right side of the board? All right. So I could also compose regular trig functions and inverse trig functions together so that they don't cancel out. For example, if I were to ask you to find the cosine of the arc sine or the inverse sine of 3/5. Right, this is a two-step process, but you can do all of this on your calculator. I would just find out what the inverse sine of 3/5 is, which I have written right here. Inverse sine of 3/5, and I'm going to do this in degrees because y'all are a little more comfortable with degrees. 36.9 degrees. Cool. So then I just plug that in. Evaluating that in my calculator, I get a value of 0.8. So one thing that might be a little more important to recognize when doing these problems is what the argument or the input of the function actually is. right? For inverse sine, right, it's going to take in, or inverse trig functions take in ratios of side lengths. Versus regular trig functions take in angles. Right? A trig function takes in an angle, spits out some ratio of side lengths. So if I go backwards, an inverse trig function takes ratios of side lengths and spits out angles. And that's what we're doing here. Inverse sine of a ratio of side lengths will spit out an angle, and I can take the cosine of that angle to spit out this, which will be 4 over 5. B over 8. We could also see this with drawing it out. We have inverse sine of 3 over 5. So inverse sine is taking something out, 3 over 5. Sine is opposite over hypotenuse. So it doesn't really matter, but it's taking in a ratio of functions. So this is going to be 5. Not sure what this is, but we'll find out that this is 4 and this is 3. If you wanted to try to draw it out, because the cosine of an angle, cosine, ca, tells you adjacent over hypotenuse. So I can just switch these, and it's still a right triangle. So if you were asked to like draw it out or something like that, you could do that too. You can go from the bottom line and then work your way back up. But that's not super important. That's just if you did want to draw it out. Cool. I will be drawing out a different example because this was highlighted in the book a couple of times, so I figured it might as well be addressed. Say for instance, I have sine of inverse cosine of x and tangent of inverse cosine of x. And the question is, how would I write these only as expressions of x being the variable? So these already are written kind of as x being the variable, but I want just a function without trig functions of x being the variable. I'll start with this one first, even though the angle for them is both the same. Remember that sine takes an angle as an argument, right? So that means that my cosine, my inverse cosine of x, is an angle. That makes sense. Inverse cosine spits out angles. So I'm going to call this some angle theta. Cool. That means that I have sine of theta. And I'm going to represent that here with a triangle. Cool. Alright. I can solve for x here. I'm going to get rid of this sine theta for a second. I can solve for x here. How would I undo inverse cosine? With regular cosine. So I have cosine of theta equals x. So theta is here. Remember that cosine is adjacent x over hypotenuse. X is equal to x over 1, so I can just call the hypotenuse 1. Cool. Now, how would I solve for this other side right here? If I'm given these two sides, how do I solve for this side? Not with a trig function. Luring you away with a trig function. I don't know what the angle is. What formula relates the three sides of a triangle with each other? Pythagorean theorem. I have a squared plus b squared equals c squared. So x squared plus b squared equals 1 squared. So b squared equals 1 minus x squared. or b equals the square root of 1 minus x squared. So that's my side right here. Cool. So now I have that my angle and my sides are represented, and I can answer some questions about them now. So I had that I'm now taking the sine of my angle, because I said that cosine inverse of x is theta. I said it right here. This is also theta. So now I'm just doing sine and tangent of my angle. Remember that sine of theta equals opposite over hypotenuse, and tangent of theta equals opposite over adjacent. So that's why it's important for me to find this opposite side, because I'm asked for the opposite sides. So this sine would be opposite square root 1 minus x squared. And then over hypotenuse 1, it's the same thing, so I'm not going to write it out. It's just divided by 1. And then opposite over adjacent, square root of 1 minus x squared over x. So that's how I could rewrite out these two functions, which are composites of inverse and regular sine or trig functions, in terms of just x. This is a little complicated, doesn't make too much sense right now, but when we revisit everything with the unit circle, this will make a little bit more sense. Specifically, any point we talk about on the circle, right, it's some coordinate x, y, and I know that the distance from the center is the square root of x squared plus y squared. You get the square root of squares, it's looking kind of similar to this thing. That's how we'll end up figuring out how to rewrite expressions of sines and cosines and everything. Specifically, we'll learn that sine theta equals y over the square root of x squared plus y squared. Cosine theta equals x over the square root of x squared plus y squared. And tan theta equals y over x for any point on the circle. But you don't have to worry about that right now. That's just some foreshadowing. This doesn't have to make sense right now. This definitely doesn't make sense right now to probably everyone. This is just kind of foreshadowing what we're going to do a bit and kind of getting you used to a little bit of what we're going to be working with either in the next week or two or so. Right. We'll do some examples with some inverse trig functions. I like these examples a little more. Oh, right. Has everyone gotten the left side of the board written down? So an example might be, I have some building. I don't know how tall a building is. And I've got a ladder leaned up against it. I know the ladder is 6 feet away from the base of the building, and the ladder itself is 20 feet tall. That's all the information I know right now. I can ask you two things. One, what is the angle? Two, how high up on the building does it go? I'm going to call this H. All right. Well, we gathered together our 5-step process. 1, what do we know? Well, if I form this triangle here, I have that the adjacent side is 6. Put 2 letters together. I have the hypotenuse is 20. And that's all I know for now. What I don't know is my angle and my height. I do, however, know that maybe my opposite equals the height, but I don't know what that is yet. So now step 3, find out some useful formulas. What are some useful formulas here? Well, I'm given adjacent and hypotenuse, and I want to figure out the opposite. So what formula relates all of the sides with each other? Pythagorean theorem. Cosine we'll use in a second, but Pythagorean theorem is what we're looking for first. Cool. I'm also looking for the angle, but I'm given all 3 sides. So I can use any of my trig functions that I want once I have my sides. Specifically, I have adjacent and hypotenuse. Those are the ones that are given to me. So to have an exact answer, I can use cosine. All right. Now step 4, I plug in my known stuff into these formulas to figure out my unknown stuff. I can first do my Pythagorean theorem to solve this point here. I have that 6 squared plus b squared, or h squared in this example, equals 20 squared. So h equals the square root of 20 squared minus 6 squared, which is approximately 19. It's 19.0 something or 18.9 something. And I can also plug in my stuff to find out my angle. I have cosine of theta equals adjacent 6 over hypotenuse 20. Solving for theta, what do I do to both sides? Inverse cosine. So I get theta equals the inverse cosine of 6 over 20, which is, did I write it down? 72.5 degrees. And that gave me really step 5 as well, solving for my unknowns, and that's what I have. I have that this angle here is 72.5 degrees. I have that the height of my building, or the height up to the building, is approximately 19 feet. Any questions about this? We're about out of time. I don't really want to worry about another problem because it's basically the exact same as this. So I'm going to leave it here today. If you have any questions, obviously, you can email me, come to my office hours, and I have them, all that sort of stuff. The recording will be on YouTube, and I will work on getting these notes typed up by the end of the week.